A building's exterior wall senses the morning sun and tilts its louvers closed. Hours later, receiving a forecast of heavy afternoon rain, it adjusts its ventilation openings on its own, without any human input. This is not a scene from a science fiction film. It is happening right now, in city centers around the world, from Singapore's Marina Bay district to London's financial core to Dubai's emerging smart city corridors. The building facade, long considered a passive finishing layer, is merging with AI and shedding that identity entirely. Today, we will dig into the core principles driving this transformation, walk through the performance data that proves its impact, and explore exactly how architects and engineers can put these systems to work in real projects. Starting now, let us start with the hard reality. In commercial buildings worldwide, heating and cooling typically accounts for more than half of total energy consumption, and the majority of that thermal load traces directly back to the building envelope: inadequate insulation, uncontrolled solar gain, and facades that simply cannot respond to changing conditions. The climate problem compounds this further. Average summer temperatures across major global urban centers have climbed measurably over the past decade, while extreme heat events, intense rainfall, and unpredictable precipitation patterns are now routine occurrences rather than rare exceptions. The annual weather assumptions embedded in a static facade design are increasingly out of date before the building even opens its doors. The fundamental flaw of conventional facade design: specify once for a fixed set of conditions, then lock it in place forever, has hit a structural limit. A building begins falling behind the climate curve the moment construction is complete. So how does an AI facade function in concrete terms? The entire system rests on three integrated layers working in continuous, unbroken feedback with one another. First, the sensing layer. Sensors distributed across the building envelope collect real-time data simultaneously: solar irradiance, wind speed, outdoor air temperature, indoor CO2 concentration, and occupancy count, all flowing in without interruption. Second, the decision layer. This incoming data stream is fused with live weather API feeds and time series energy pricing data. An AI algorithm then calculates, in cycles as short as 1/10 of a second, the precise control target that minimizes cooling and heating load at any given moment under any given set of conditions. Third, the actuation layer. Electric actuators respond immediately, adjusting electrochromic glass tint levels, repositioning external louver angles, or opening and closing natural ventilation ports as directed. When these three layers cycle without interruption, the facade transitions from a fixed boundary into a continuously optimizing, living skin. Numbers tell this story more clearly than any description. Consider a representative office building of 10,000 square meters of gross floor area, a scale common to mid-rise commercial developments across most major markets worldwide. A standard curtain wall facade produces approximately 320 megawatt-hours of annual cooling energy demand under typical operating conditions. Upgrading to a passive, high-performance, low-emissivity glass facade brings that figure down to roughly 240 megawatt-hours, a meaningful improvement. But still working within the limits of a fixed system. Apply an AI-controlled adaptive facade, and demand drops further to approximately 190 megawatt-hours, an additional 21% reduction over the passive glass solution, and more than 40% below the conventional curtain wall baseline. Carbon emissions follow the same downward curve. International green building frameworks, from LEED and BREEAM to the EU's Energy Performance of Buildings Directive and the IEA's Global Net Zero Pathway, are increasingly treating this level of dynamic envelope performance not as a premium specification option, but as an expected compliance threshold for new construction projects targeting 2030 net zero commitments. Theory is useful. Tools are what move projects forward. The good news is that a mature ecosystem of software platforms and hardware systems already exists for implementing AI-driven adaptive facades, and they are accessible to architects and engineers working in any market today. First, Climata. This Netherlands-based facade climate simulation platform integrates with regional weather datasets and uses AI to automatically optimize louver geometry and shading strategy. It connects natively with Revit, allowing design teams to review optimization outputs directly within their existing BIM workflow. Second, radiance, the established industry standard for daylight analysis and glare prediction. Radiance allows detailed simulation of facade control scenarios before a single product is specified or a single detail is drawn. Third, Autodesk Format, combined with Energy Plus. Among the most accessible combinations for early-stage massing and facade performance evaluation. This pairing supports AI-assisted review from the first schematic decisions, not just at the end of design development. Fourth, at the product level, Saint-Gobain's SGG connected glass range and the Sage Glass electrochromic system are accumulating a growing base of completed project references across Europe, the Middle East, and Asia. It is worth noting that BIM integrated AI review tools now detect approximately 78% of design coordination errors at the initial review stage, a capability that significantly reduces costly downstream conflicts when adaptive systems interact with structure and services. No technology story is complete without an honest account of the friction. Real barriers to adoption exist at the project level, and understanding them clearly is the necessary first step to navigating them effectively. The most significant is upfront cost. AI facade systems carry an average construction cost premium of roughly 1.8 times that of a conventional curtain wall system on a per square meter basis. That number makes developer and client conversations challenging without a compelling, evidence-based financial narrative to accompany it. Lifecycle cost analysis fundamentally reframes that conversation. When energy savings over the building's operational life, reduced maintenance expenditure, and rental premiums from green building certification are aggregated, the investment payback period runs approximately 7 to 9 years, a horizon that fits within the financial models of most institutional building owners. The second barrier is a maintenance skills gap. AI facade systems require periodic software updates and sensor recalibration, a specialized discipline for which the service and commissioning ecosystem is still developing in most markets globally. Neither of these barriers resolves quickly or easily. But that is precisely what creates the strategic opportunity for firms that move early. Those who build expertise, establish repeatable workflows, and develop credible case studies now will be the natural partners of choice when regulatory pressure accelerates adoption as it will. We have covered the operating principles of AI facade engineering, the performance data that quantifies its real-world impact, the tools and platforms available for implementation today, and the barriers that define the actual shape of the market opportunity. The conclusion is unambiguous. The building facade is no longer a static finishing element locked into place at project completion. It is evolving into a living system, one that reads atmospheric conditions in real time, responds continuously to occupant behavior, and optimizes its own energy performance without human intervention. As net zero building regulations tighten across global markets through 2030 and beyond, AI-driven adaptive facades will complete their transition from premium specification to baseline requirement for code-compliant new construction. The designers, engineers, and firms that invest in understanding these systems now, who experiment with the workflows, build the early project references, and develop the maintenance expertise before the mandates arrive, will define what intelligent buildings look like for the next generation. How are you thinking about redefining the facade in your next project? Share your approach in the comments below.